Okay, started.
All right, hello, welcome. This is the volume populators meeting in the Kubernetes storage SIG. Thank you for joining. So as I mentioned last week, I have everything basically working, and at least yeah, just to recap, my efforts recently have been going into the actual example populator and refactoring it, and with the help of several community members last week, I was able to refactor this and get it in a shape I'm pretty happy with. So what I wanted to do today was to sort of go through the code and talk about what it does, how it does it. Um, there's a few remaining things that, you know, maybe some sort of polish that is still TBD, but basically I think we could go to beta with this version of the code. Um, so um, but before I jump into that, is there any questions or anyone new that wants to ask about something else before we go into the code? All right. So if you look at the agenda, last week has a link to the Git repo where the code is. You can go there and look and follow along if you want to. But I'm just gonna share my IDE here. Um, is that visible to everybody?
Yeah.
Okay. So there's this repo basically has two Go files. It has main.go and controller.go. Main.go is the sort of the sample for this hello world data populator. It's only 115 lines. It's very short. So this is sort of the minimum required to implement a populator, not including all the auto-generated code for the hello object, which is in this client directory. You know, the auto-generated stuff is a huge amount of code. And then there's the controller.go, which is, if I can't see my scroll bar, here it is, about 758 lines. This is the reusable part. The idea is that this will eventually be a library that will be imported by all of the populators and will implement sort of the core Kubernetes API interactions in a consistent way that sort of follows the, you know, the rules and I guess the requirements of any kind of volume provisioning that we'll talk about in a minute. So and then the rest of this repo is just boilerplate stuff, you know, go.mod with minimal requirements. Come on, open, you know, these minimal requirements. Eventually, I'm hoping to host this under Kubernetes CSI. It's not here yet. There's a make file, there's a Docker file. These are all minimal. There's a Kubernetes deployment YAML that demonstrates how to deploy it. But I want to go through the Go code and talk about what it would look like to actually implement a populator. So I'm going to start here in main.go. There's just three functions here. The main function does all the arg parsing. So these things here are pretty standard. The kube config and the master, you know, you see this almost with every Kubernetes sidecar to specify how to talk to the Kubernetes server. There is an image name, which as I'm realizing now, probably doesn't need to be a command line parameter, but this tells the populator what is going to be the image name for the pod that'll be doing the population. There's a version command. There's this main switch called mode, which tells this. So this binary is a dual purpose binary. It is both the controller and the populator. And which identity it takes on depends on whether you run it in controller mode or populate mode. And then if it's in the populate mode, you have these two special arguments that are specific to the hello world populator, file name and file contents, that specify which file will be created and what will be put into that file. All right. So instantiating a populator is as simple as this one-liner here, populator machinery.run controller. You give it the master URL, the kube config, the image name, that's a command line parameter here, the namespace where it will be running, the prefix, which is what gets prefixed onto all the annotations and finalizers that the populator will be creating. a group kind, and a group version resource object. These are just standard Kubernetes boilerplate things. The mount path and the device path within the pod of the volume that to be populated. So this is how you control, you know, when the populator pod starts up, where will the sort of the temporary PVC get mounted in. And then there's this function called get populator pod args, which is down here at the bottom. So the idea behind this function is that for any given object to populate, you want to invoke the populator pod with different arguments. And right now, and this part I envision changing over time, becoming more flexible. This is sort of the minimum that was needed to sort of get this off the ground. The idea is it's a function pointer. It takes a Boolean, whether this is raw block or not, and then the pointer to the actual object. And in this version, it's an unstructured, because the populator machinery doesn't have the access to the code generator, and so all of the objects it deals with are unstructured. And then from this, it expects you to return a list of arguments or an error. The first thing it does is we convert the unstructured to a hello object, which it's expected to be, because of the GK and the GVR up here are both for hello v1. And then it basically just returns a list of arguments that the populator pod will have. So it'll put it in mode populate, it'll set a file name. The file name is different depending on whether it's raw blocks or not. It has a file contents, which is just a string, which in all my examples is just hello. And that's it. And then the populator machinery will instantiate a pod after a volume has been created. It will attach the volume to the pod, and then it will invoke this binary again with the mode populate argument, which will cause it to call this function called populate, which gets the file name and the file contents, and it just opens the file, writes the contents in, and it's done. So it's really simple. This is a sort of the minimal example of how to create a populator, and the idea is this can get as fancy as you want, but you know, if users you know, deploy this thing and they deploy the CRD that represents the hello object, all they need to do then is instantiate instances of the hello object, use them as the data source of a PVC, and this will do the rest. It'll be all taken care of. And to answer a question that Shing asked a while ago, if there are populators where the actual work is done by some CSI driver, or some sort of, it's done by the backend itself, we could still use this model here, where you have the populator machinery running, and basically the pods that it creates, much like in this example, it's only about 20 lines of code to do the population. This could be a no-op, or a call, or an API call to something else to actually do the real work. So just because we've set this up as a pod that attaches to the volume, doesn't mean that you can't populate using some external thing that knows how to talk to the storage controller and do the real work. So before I go to the actual populator machinery, any questions about this code? And someone's got to go off mute and tell me that you can hear me, so I know I'm not just talking to an empty room.
We can hear you.
Okay.
Thank you.
All right, good. All right. So if no questions on this, the populator machinery itself, as I said, is, how can I move this thing? Okay. 700 lines or so. Got a couple constants. The struct itself has several informers, because it's going to be watching PVCs and PVs and pods and storage classes, and this unstructured object, which represents the data source CRDs themselves, that this thing doesn't know any, it just treats it as an unstructured thing. So there's only one public method in this whole thing called run controller, which is the one I described above on main. And this thing just does the normal Kubernetes controller setup, it gets the kube config, it instantiates some kube clients, it makes the factories. We have 5 specific informers that get created here, and it builds the objects, and then it sets up watches on all 5 of those object types with little handler functions that are, most of these handler functions are extremely simple, as you'll see. Now there's this notification framework I built in here that basically allows, the only thing that this controller is interested in is PVCs, really. It's going to see a new PVC that it determines needs to be populated. If it determines it doesn't need to be populated, it just drops it and ignores it and lets the regular thing happen. But if it determines that it does need to do something with the PVC, it starts processing the PVC, and then if it encounters a reference to a PV or a storage class or a pod or another PVC that doesn't exist yet or isn't in the right state yet, it sets up a notification for itself with this add notification method. So, and then when the other watchers for those other objects see something happen on that specific object, it'll run the sync function for the original PVC that was interested in it again. So this basically allows me to watch all the different kinds of objects related to a PVC and with only one sync function, and keeps the code relatively small and simple. There's a cleanup that cleans up all the stuff that this thing creates. I won't go through the details of this because it's just manipulating sets. Translate object figures out whether it's a real object or a tombstone. Handle mapped. This is the thing that unmaps objects. So down here, if we get a PV, like if the PV watcher sees a change to a PV, most of these do is call handle mapped. And then what these do is they go look for those notifications to see if there's any PVCs that are mapped to this PV, it'll do something. Similar with pods, storage classes, and unstructured objects. The only interesting one is handle PVC. It both calls handle mapped for PVC, and then it also does the translate object, and then it adds the real PVC to the work queue. The run function, this is just where it forks the background thread to do the actual work. This is pretty standard controller stuff. The run worker is the background thread that is pulling things off the work queue. This thing has a little bit of parsing of the keys. It figures out if it's a PVC, and if so, it calls sync PVC. Everything else is an error. Not too interesting. Sync PVC is where all the real work is. So this is about half the file is this giant sync PVC method. And I'll go through this all the way to sort of explain every case that it gets handled, and you guys can help me remember if I missed any important cases. So most importantly, it ignores any PVC in its working namespace. So every populator is going to need sort of its own namespace where it creates these temporary PVCs that it's going to do the population on, and then after those PVCs are populated, it's going to rebind the underlying PV back to the real PVC. And so because of that, you can't ever create a PVC with the data source in the same namespace where the populator for that data source lives, because that would be really weird. So we just ignore those if it somehow happens. It gets this is just a, get the actual PVC from Kubernetes. The first thing we do when we get a PVC that is not in the wrong namespace is look at the data source. If there's no data source, or if the data source doesn't match our GK, the group kind of that this populator is responsible for, it just ignores it, and it's done. So we'll never look at that PVC again until it comes back in through the watcher to get synced. So this is a very lightweight way to ignore things that are not interesting to us. If it does match the group kind that this populator is responsible for, the first thing it does is it goes and it loads that the unstructured object, which is the actual data source. And if for some reason it doesn't exist yet, we bail with after adding a notification on that unstructured object that will tell us when it does exist. So this is the case if someone creates the PVC and points to data source before they create the data source itself. So when the data source gets created, this notification will fire and we'll come back into the top and handle this again. Here's all the wait for first consumer logic. It's not that bad. So first we attempt to determine if there is a storage class name. If there is a storage class name, we try to get the storage class. And again, if the storage class doesn't exist for whatever reason, we add a notification and bail so that when the storage class is eventually added, we will come back in and reprocess this. But if there is a storage class and we're able to get it, and it has a volume binding mode of wait for first consumer, we set wait for first consumer to true, and then we look at the node name of the PVC. So this is something I actually wanted to talk to you guys about. I went looking at how wait for first consumer is actually handled in the real external provisioner Sidecar, and what appears to happen is it relies on this annotation called selected node. So what happens is if there is a PVC and wait for first consumer is set to true, and this annotation is not set, the external provisioner won't do anything. And so something then is watching that PVC and waiting for a pod to get provisioned and bind to that PVC, and then waits for that pod to get scheduled to a node. And then when that node gets set, it sets an annotation on the PVC. And I don't know which component is responsible for that portion of the work. But
I think it's the scheduler.
The scheduler itself.
Mm-hmm.
Okay, that would make sense. I think that was what I suspected after looking at that code, but I couldn't find the actual code to do it, and I didn't look too hard. So what this check here is doing is basically checking, has the scheduler put that annotation on yet? And if not, we just wait. We don't do anything. So if wait for first consumer set to true and the scheduler hasn't put the annotation on, we're not going to do anything, which is exactly what the external provisioner would do. If it is set, then we'll continue on. Or if wait for first consumer is false, or there is no storage class, it will assume it's false, and then it will continue on with the immediate binding strategy. So we automatically generate the pod name and the PVC Prime name, just based on some prefix and then the UUID of the user generated PVC. This is currently hard-coded. This could be made more flexible depending on if we want to. We set up notifications on both those objects so that if this pod doesn't exist or if it changes later on, we'll get the chance to resync this PVC again. And then we attempt to get the pod and get the PVC. It's okay if these don't exist yet because we are responsible for creating them. So if they don't exist, these variables just get set to nil and we keep going. So I put a comment for myself here. At this point, we haven't changed anything. We haven't done anything. We're just reading, checking a bunch of different objects. Starting here, we're going to start manipulating objects. So the first main switch is whether the PVC that the user created has a volume name or not. So if this volume name is set, it means that somehow the PVC got bound to a PV, and whether we did it or someone else did it, it can never be changed. So we assume that we're done, and we skip over the main portion of this function. If it's empty, then this PVC is not bound yet, and there's work for us to do. So the first thing we do is we put a finalizer on the user's PVC that says we're working on it. And this function is down at the bottom of the file. I went through a lot of gyrations for how to implement this ensure finalizer function. I ultimately decided to use patch with the JSON patch to add it on. It's kind of difficult to do this atomically because the representation of the finalizers is a list, and patches in Kubernetes can't atomically manipulate lists, or they can, but if there's a race, you can get really weird behavior. So this is my attempt to safely atomically update the list of finalizers with a JSON patch. I can read through that if you're interested. Where was I? Ensure finalizer. Okay. Okay, so the first thing we do, if the pod doesn't exist, the populator pod, we create it. Um, here we look at whether the user created a persistent volume. So we support file system volumes and raw block volumes here. Depending on whether it's raw block or not, it could change the arguments that the populator is going to need. So we include that flag. This is the callback function to get populator args that's defined in main.go. Then we create the pod. We assign it to the PVC name that we're going to use. It has one container in it. The image name is defined by that command line argument. The arguments are defined by this callback. Whether it's raw block or not, we set up either a volume device or a volume mount. If it's wait for first consumer, we set the node name on the pod to the node name that the scheduler chose. So this forces the resulting pod onto the node where it needs to be, basically bypassing the scheduler for this populator pod. Then it creates it, and we're done. Then it goes ahead and creates the PVC for that pod. Again, it checks if it already exists. If it doesn't, we go through the process of creating it. If wait for first consumer is set. If wait for first consumer is set, then for PVC Prime, what we do is we put the annotation on PVC Prime with the same node name that the scheduler chose for the original PVC. And I presume this to be safe. I've tested it. It seems to work. I don't know if it has any weird bad interactions with the scheduler. I hope it doesn't. But this worked when I tested it. Create the PVC, we're done. At this point, we always return because there's no chance that the rest of this function will succeed if we're just creating the PVC and the pod. So we return, we wait for something to get updated. The sync function comes back through, and oh, it's right. Sorry, this return is only if the pod was nil. So if we're creating the pod during this iteration of the sync, then we always return. Once the pod gets created, we'll come back through from the top, and this will be false. So we'll skip over this section. At this point, we'll be looking at the pod status. If it's not succeeded, then if it's failed, we're going to delete the pod and then return, which will cause that pod to go away. The sync will get called again. It will recreate the pod, and it will do that in an endless loop until we reach succeeded. If it's not succeeded or not failed, it will just return and wait for it to be something other than those two. It will wait for it to be one of those two, I mean. So while it's pending, it just keeps looping. So at this point, we know that the pod has succeeded. If it gets to this point, PVC Prime really should not be nil if the pod has succeeded, because the pod needed that PVC. So this is just an error if the PVC isn't there. At this point, so once we get here, the PV exists and has the data in it. So it has been populated. We're basically done. We just need to do the rebind and cleanup. So here we add a notification on the resulting PV for that PVC Prime, which must exist because it's been populated by this point. And then we get the PV. If for whatever reason it doesn't exist, we bail and wait for it to exist. And then here we look at the claim ref on the original PVC the user created and basically compare it to the PV that PVC Prime was bound to. And if they match, then we're just waiting for the rebind controller to do its thing. If they don't match, then we're going to build a patch on the PV that basically rebinds the PV back to the original PVC that the user created. And here I use a strategic merge patch to do that. And then again, if we're doing a rebind, we always return because we have to wait for the bind controller to do its work. And then again, we come in from the top, and when we come down through here, what we would expect during that iteration is for pvc.spec.volume name to not be empty, because at that point, the PVC bind controller will have updated the volume name of the original PVC to point to the PV that got created. And you'll come all the way down here And here's our pointer to PVC. So what we're waiting for here is for PVC Prime to go into the claim lost phase, which is what will happen to the PVC after we rebind the PV out from under it, is it'll become lost. And once that happens, that's our signal that the rebind is done and it's safe for us to do cleanup. So again, I wrote a comment to myself saying that. Here's where we delete the pod. Here's where we delete the PVC. Here's where we remove the finalizer on the original PVC. And at that point, we just clean up our in-memory data structures and we're done. That's the whole thing.
Can you go back to the rebinding logic? Is that?
Yeah.
Is it safe to do that if it's binding to the wrong PVC? So here you're trying to correct it. Is that safe to?
Well, I wouldn't call it wrong. So here we're obtaining a pointer to the current PV's claim ref,
Okay.
which initially will be PVC Prime, the PVC that we created in our working namespace and the PVC that we attached our Populator pod to. So that's not wrong. It's just not what we ultimately want it to be. So so here we're comparing the name, the namespace, and the UID of the claim ref that is currently on the PV. And what we're comparing it to is the actual PV that the user created. So initially, it's not going to be these values. It's going to be the name and namespace and UID of PVC Prime, because it was created through the normal process by some CSI controller, some CSI external provisioner created this PV. You know, as at our request, because we created PVC Prime in our special namespace. So the normal thing happened, and that PV got correctly bound to PVC Prime. So what we're doing here is constructing a strategic merge patch that refers back to the original PVC's namespace, name, UID, and resource version. We're setting an annotation called populated from on the PV, just as a reminder to ourselves that this PV has been populated from this specific data source name, and then it executes a JSON patch with the strategic merge patch. And the only thing that's in here is the annotations, the name, and the claim ref. So the rest of the PV is empty and will not get overwritten. It'll just overwrite the claim ref. And this works perfectly well. Nothing prevents you from changing the claim ref on a PV.
I have a question related. I'm not sure if I missed this detail, but it looked like the PV will be created when you try to populate the data to it by the populator, right?
Well, so let's go back up here and I'll go through this carefully. So first we construct the pod with a regular pod create. And we construct the PVC, and of course the pod refers to the PVC, and then we go into this wait loop where we're waiting for the pod to get done. So in that waiting time, it's presumed that something is actually creating the PV for that PVC, because the pod couldn't have started and run to completion unless that happened.
Yeah, I think I understand that part is it will be automatically, dynamically allocated. The PV will be, but there's some, I remember I run into this problem in the past that the user might want to create the PV, you know, that have some node affiliation to specify the node that it kind of have to be, because of some of the storage might have some of that requirement. But you know, do you have any plan to add any kind of affiliation here in this area for the PV creation when you do this PVC?
Okay, so your main question is about locking the PVC to a node. Is that like how?
Yeah.
Okay, so
if the user have that requirement, right, how would you handle it here?
So that's actually a good point. So if wait for first consumer is set to true, I copy the semantics of wait for first consumer by waiting for this annotation to pop up. But you're right, there are other ways that the system can force a PVC onto a node, and this code needs to replicate those semantics as well. So I need to go look at the other ways that I think a storage class can have sort of allowed topologies and stuff that can force the PVC on. Well, okay, so if the storage class had an allowed topology, when we construct PVC Prime here, we copy the storage class name from the original PVC. So any sort of behavior determined by the storage class will get inherited by a PVC Prime because we copy the storage class name onto PVC Prime. So that might cover all of the topology related use cases where the storage class has a specific topology encoded in it and the scheduler has to respect that. You should get it just by copying the storage class itself. The only thing that definitely needs to be replicated here was the wait for first consumer, because that's a dynamic thing where it just depends on the luck of where the pod gets scheduled. Then the PVC has to follow the pod, and so we replicate that logic here, as I showed, right up here. If wait for first consumer, then we get the node name out of the PVC annotation, and we wait for it to not be empty. So does that answer your question? I'm pretty sure the only two ways a PVC can get forced onto a node are either through wait for first consumer or by explicit
this code
topology
is going to
setting.
hold off. Mm-hmm.
Huh?
This code is going to hold off until the selected node is filled in.
Yeah. If the volume binding mode is wait for first consumer and the node name is an empty string, it'll just return and it'll wait for that annotation to get set to something.
And so once that gets set to something, how does the external, or is this modifying the external provisioner? This is not modifying the external provisioner, right? This is a standalone controller.
Yeah, once node name is set to something, there's two things that happen. One, the pod, where's the line? The pod.spec.node name gets set to that value. So the populator pod gets forced onto the node that was chosen for the original PVC. And similarly, we set the annotation on the PVC we create to the same. Those two things seem to be enough to force the correct behavior.
How does the external provisioner know to stand down?
Well, it's gonna follow its same logic where the PVC Prime will be of the same storage class, and so it will also see that PVC Prime has wait for first consumer equals true.
Mm-hmm.
And what it should do then is wait for this annotation to get set the way it always does. And so because we set it, it knows what to do. It doesn't need to wait it because we just, at creation time, we fill in that annotation. And so it immediately knows it can get to work on putting it on that node.
But how does it know not to respond to the original PVC?
Well, that's the whole logic that already exists. And we actually fixed a bug in the latest Sidecar release where if it looks at the data source and it doesn't understand it, it's going to ignore it.
Perfect.
So the original
okay.
PVC has a data source that the Sidecar doesn't know about, and so it says, I can't populate this. It will generate an event, I think, or a log message. I think both an event and a log message saying unknown data source waiting for populator to do its thing or something like that.
Got it.
Yeah, it's going to ignore the first PVC. It won't ignore PVC Prime because there is no data source on PVC Prime, but because we copy the node name, annotation, and the storage class name, that's enough to sort of tell it wait for first consumer is also true on PVC Prime, and so you better put it on that node.
Okay, makes sense.
So,
I think it would be good to get.
Go ahead.
I was going to say it would be good to get Jan's eyes on this code as well, since he wrote the original PVC controller. He's probably aware of some subtleties, but overall looks good to me.
Okay. Yeah, my big worry would be that that somehow the scheduler might attempt to muck with this annotation that we're setting.
Yeah, I think once it's set, it shouldn't be. It's worth investigating. I want to say it shouldn't, but it's worth investigating.
I tested it and I didn't see any problems, but yes, it would be good to get a triple check to see that that this
Is
actually
there
works
like
out.
a race between the scheduler and this controller though? I mean,
No, because this is already set at creation time. So by the time the object shows up in the API server, it's going to have the annotation in it. This is not added afterwards. It's part of
okay,
the
so you're
create.
saying that the schedule should not even be attempting.
Right. Yeah, and similarly with the pod, we're setting the node name
Mhm.
at creation time, so the scheduler will believe there's no work to be done on this pod.
Okay.
It'll just say, oh, it has a node name, you know, it's a no op for me. The scheduler only reacts to pods that don't have node names, I think. So yeah, I'm pretty sure that this is safe. So and we lost Fong, the guy who asked the question. He seems to have dropped off. I was going to ask if he was satisfied. I guess he is. I hope he is. Any other questions?
No, this looks good. I think moving forward, not necessarily for alpha, but maybe for beta, it would be interesting to think through how we could extract this out into a sidecar. And I think one of the benefits of that would be, you know, just the fact that this is such complicated logic. I'm sure this is gonna.
It's a little complicated, but like so I was able to remove a lot of complexities. I went over and over and over this code, removing stuff that wasn't strictly necessary for correct behavior. And I got it down to about 750 lines, which I feel like is not that bad complexity-wise.
It's not too bad, but I suspect that eventually there might be future changes we want to make here.
Yes.
If this is in a kind of standalone sidecar container, then it becomes much easier to integrate versus like, oh, let me go grab a new library, recompile everything, and you know, that kind of thing.
Yeah. So and we talked about this before. I agree
Mhm.
that having a sidecar is better from a deployment perspective because it means that we can like fix bugs in this code without having to recompile all the populators, which would be nice. The downside is going to be that instead of just having code that links and has a callback, we're going to have a full gRPC interface with a socket in the middle.
That's what I'm thinking about. Maybe if we think about what that interface should look like, do we need a full-blown gRPC interface, or could we get away with some like soft contract that says, you know, hey, I will surface a local you know, file system directory at a specific location. You fill it with all your data, and, you know, I don't know, give me some signal somehow that you are complete. And once that happens, then your side of the contract is fulfilled, and I'll carry on as the sidecar. Something like that.
There's two touch points. There's at creation time, the specific populator has to tell the current library, you know, a bunch of variables like image name, various paths, you know, the group kind and group version resource information. All that could be in any format you wanted. In fact, it wouldn't be hard to make this a gRPC call. The problem is the function callback, where for each specific data source instance, the library or the sidecar is going to have to sort of ask the populator, like, how do I set up the specific pod for this object? You know, what arguments do I need to set? What do I need to? And I was considering making this even more fancy, where we actually send back the whole pod instance to the populator and let it manipulate the pod instance, so that it would have more flexibility for exactly how that pod gets constructed. I didn't do that in this version of it because I was trying to keep it simple. But yeah, we want to make sure that the individual populators have the right amount of control over how that populator pod gets instantiated for an individual data source. I mean, it's conceivable that like it may want to add other PVCs or other things. When Cozy comes along, it's conceivable that like you want to do Cozy stuff here. I really don't know like how much control the populator will need over the pod that gets created. Right now, command line arguments are enough, but if it gets much more complicated than that, like doing it through any file system mechanism or gRPC would both be kind of nasty, because you want to pass in the instance of the object, which is the data source, from the populator library to the, or from the machinery, I guess, to the populator, and then get back, you know, what features the pod needs to have. And yeah, right now it's easy to do because it's all Golang and it's a callback, and I can pass back and forth whatever I want. I don't. You're gonna have to, I guess, explain, Saad, what you mean by the like some sort of a file system, because I'm just trying to think that.
Yeah,
through, like,
no, I hadn't thought through kind of these other touch points. I was really only thinking about having to write the data.
okay,
And
yeah, yeah. I
so,
mean, it's
yeah.
I mean, it's only one touch point, but it's a very gnarly one.
Mm-hmm.
If this was a gRPC, there would only be two gRPCs. There'd be one going one way and one going the other way.
Yep.
But
then we still got to think about where that would exist, and backwards compatibility and getting that API right. So
yes,
maybe like for alpha, let's hold off on that. Do the simplest solution possible. Get it out there, see how kind of viable it is, and then a goal for beta would be come back and revisit and see if we can make this modular.
Yes, I totally agree. Like someday it would be nice to have a sidecar. I am having a hard time.
I thought we are trying to go beta, right, with the implementation, right? It's already alpha, right?
Well, the part of it that I want to go beta is the feature gate.
Okay.
And that, to do that, is going to require the other work that I was doing before the holidays, which is that's populator controller and the registration of populators that basically lets deployers sort of register the populators with the system, and it gives users feedback when they specify a data source that isn't valid. They're told that. If we can just get those pieces in, then the feature gate, the any data source feature gate, could go to beta, because we would have appropriate error messages, and we would have all the other things we would want to have to convince, the API guys that, like, we know what we're doing and this is eventually going to work. And then this could be delivered as alpha while the feature gate is in beta, and we can iterate on it.
It's a little confusing.
I know it's confusing. So I'm gonna.
Should just pick one. I mean, if you say that their feature gate is beta and this is alpha, then maybe a little confused. Maybe we should just say beta then. The beta you can have like beta 1, beta 2, right? So like.
We may need to wait another cycle to get to beta, but I'm going to make the case that it is safe to go to beta now, while this is still alpha, because.
But I'm just saying that what I'm proposing is not to say this is the alpha. Maybe just say like the beta 1, beta 2, right? You could do that, like we run beta 1.
Okay, yeah.
Something
how
like that,
we label
right?
this?
because
this is all out of tree and really just sample code at this point in time. Yes, we could call it beta, and we could iterate on it while it's beta, because it's out of tree. But yeah, I am very focused on getting enough stuff sort of as a proof of concept so that the in-tree part can move from alpha to beta now.
Yeah, I agree. I just thinking it will be a little confusing. We're talking about both beta and alpha in the same feature.
Yes, I know. Yes. I will try to wordsmith that in the KEP and answer any questions. But I'm glad you brought it up. So what I was going to say is this is good enough for me at this point. I'm going to this is already pushed to GitHub at the moment, and it's done. And so my next piece of work is to get the KEP in shape and merged. So I'm going to go back and do all the PRR stuff and
another related question, maybe not necessarily this one, facade. Like we have some of those features, right? We don't really have a feature gate, and then we go alpha and then beta, like the volume health one. I'm not sure, like, how do we say it's alpha and beta? We don't really have a feature gate to these.
So I think it gets tricky. What we did with CSI was when there was not a direct feature gate in the core Kubernetes, we updated the CSI feature documentation to say, oh, such and such feature that's part of CSI is, alpha, beta, or GA. So there was somewhere where the user can track what the actual kind of state was.
Okay.
And so I'm thinking Populator is one of those kind of extension mechanisms like CSI. So especially if we start going down this direction of, oh, make it modular with a sidecar and, you know, some sort of gRPC interface, we're talking about probably 1 or 2 additional repos to manage all of this. And I imagine that repo would have kind of developer documentation as well.
Yeah.
And so in that developer documentation, we can say the status of the populators is such and such.
Okay.
So that then it's just SIG Storage making a declaration that it's alpha, beta, or GA.
Right.
And we follow our own
And
rules.
we make it clear, you know, like you said, in the kind of Kubernetes API side that, you know, this is not necessarily linked to Populator, the flag that we have. It's more just a kind of opening it up to the world kind of thing. And you have to evaluate each individual data source on its own merits.
Yeah, yeah. Yeah, because once we get the sidecar, or sorry, the feature gate to beta and deliver the Populator controller and the data, what do we call it? The I think it's just called volume Populator CRD. Once that's delivered, other people could make other implementations of volume populators that share none of this code, and there was nothing to prevent that from happening.
Yep. Yeah, I think this would be worthy of a blog post at the end of this release, just to clarify this whole picture.
Yes, I agree. That would be a good way to communicate. Okay, so yeah, I think we covered everything we need to, and yeah, so I'm gonna focus on the KEP, getting that in merged by the KEP deadline, and then turning my attention back to the pieces that actually need to merge for the feature to go beta, and then this, you know, there was one other thing I wanted to mention, which is this existing version of the code has no logging. I didn't put any logging in because I couldn't choose a logging library. So that's work to be done to add logging and to make it do something other than panic when there's an error. I was just looking at the screen here, you can see it just panics if anything goes wrong, which is not the best error handling mechanism. So that needs to be shored up, but yeah, I just left logging out for the first version, and there's no unit test or any of that stuff. So those kinds of things are obviously needed before you would ship this thing.
And so next steps here are to shore up the KEP, or?
Yeah, I'm going to leave this hello populator in the state that it's in, because it's a good sample. It's already importable in some form. If somebody else wanted to write a populator, this library is usable now. It will mostly behave correctly. You know, in all the cases I tested, it works. So it's actually usable in some sort of an alpha state right now. And yeah, I'm going to go then work on the populator controller and the volume populator CRDs that actually need to ship in a beta form, much like the snapshot controller and the snapshot CRD needed to ship so that deployers could actually deploy that snapshot controller and snapshot CRD with their Kubernetes distros when the snapshot feature went to beta back in 1.17. And you remember that it was a debacle because not everyone actually did that.
Yep.
So we're going to have to go through that again in 1.21 with this feature, assuming that we meet all of our deadlines and everything does happen as planned. I think we can hit beta in 1.21, and we'll just have to ensure that that controller and that CRD get included in various distros as they move to 1.21.
Okay.
All right. So that's all I have for today. We used up most of the time, so you don't get any time back. Sorry.
All right. Thank you.
Plan on meeting again next week, and I'll talk about the status of the KEP.
Sounds good. Take care.
Thank you.
All right. Thank you, guys.
Bye.